We just got done talking about the factor theorem, which says x minus c is a factor if we can do synthetic division and get a remainder of 0. Or also, if you plug that number into the function and get an answer that's 0, that means when the x value is a number c, the y value is 0, that must be an x-intercept, or sometimes we call those zeros or roots. Okay, the next thing we need to learn is called the rational roots theorem. Now again, like I just said, zeros, roots, x-intercepts, those are all names for the same thing. The reason we call them zeros is because they're where y equals 0. The reason we call them x-intercepts is because that's where they cross the x-axis. The reason we call them roots is because they are at the root of the function. They are the essential pieces that create that function and make it what it is. Okay, so if we want to find the roots of a function, we need to find those points where it crosses the x-axis or makes the y value 0. There can be any number of roots, and sometimes it can be difficult to find all of them, especially when there's a potential of there being so many. Now with graphing calculators these days, it makes the process much easier to eliminate roots that aren't going to work and find the ones that will. Let me just remind you of the word rational. The word rational means something that can be written as a fraction. Roots can be imaginary. Roots can have a square root in them because they can be found by using the quadratic formula, which ends up having a square root in it. Anytime you have a square root where you cannot simplify the square root, your root is irrational. So we're going to learn a theorem that would help us to find rational roots only. And what it does is it helps us to narrow down the choices of the roots or zeros that we are trying to find. Okay, so what we do is, for a function qx to some power, I'm kind of making this up as I go because I'm trying to word it a little differently, but I don't know if it's going to work. So some power here plus something to some power here plus something to x to whatever power plus p. What you do to find the potential rational zeros is to take the number p and factor it, and then take the number q and factor it. And then to find those potential rational zeros, you're going to take all the factors of p and divide it by all the possible factors of q. And that will give you your potential roots for that polynomial function. This is going to make a lot more sense if we do an example. Okay. Two x to the third minus 3x squared minus 3x minus 5. Alright, q in this problem is 2, 5 in this, or p in this problem is 5, or negative 5, whatever. So what are all possible factors of p? Well, negative 5 is p, so we do all possible factors of p. All possible factors of p would be 5 and 1, or negative 5 and 1, and then positive 5 and negative 1. Now if the number 5 had been more like an 8, then we would have 4, positive and negative 4, positive and negative 2, positive and negative 1, positive and negative 8. It increases the number of factors if you have a number that's not prime. If the number is prime, then you just have 4 possibilities. What are all the possible factors of 2? Well, there's 2 and 1, or negative 2 and negative 1, right? So now using that, we need to figure out what all of the potential rational zeros are. Now this is a little confusing with all of the pluses and minuses, so I kind of just put a plus or minus out front, realize I'm going to use the numbers 1 and 5, and I'm going to use the numbers 1 and 2, and then I figure out the combination of possibilities. So I can have 1 over 1, I can have 1 over 2, I can have 5 over 1, and I can have 5 over 2. And in each case, each possibility could be positive or negative. So those are the possible rational zeros that this function might have. It might or might not. These are just the only possible ones. So this narrows down how many choices we have to try once we start using synthetic division to see what divides into the function and what does not. So that we would only try these 8 possibilities instead of trying infinitely many possibilities to find the answer. Of course, at that point we would turn to a graphing calculator because it would become ridiculous to try and do without, which is how I learned this more or less back in the day. Which is why this particular theorem was a great one to have back before that lovely technology. Alright. Our video is already 6 minutes, so I'm going to leave this one here.